Good morning. All right. So last day we talked about, we introduced polynomials, right? And we talked about the end behavior polynomials. And then we said, well, now let's take it back a step and let's just talk about polynomials degree 2 for a little bit, which are quadratic functions. Okay, so I guess not much of a review, but we introduced polynomials. That's big. Polynomials when we have multiple terms of different powers. And so today we will focus on polynomials degree 2. Which look like f of x is, I'll do a2 x to the power of 2 plus a1 x to the power of 1 plus a0 x to the power of 0. But usually, oh, that doesn't look like an a, does it? But usually we don't write the power of 1 and the power of 0 because that just is 1. So what we end up with is a2 x to the power of 2 plus a1 x plus a0, right? If we just recall that x to the power of 0 is 1. Right? Okay. Quadratic functions are pretty fun. Back to basics. Yeah, disbelief. I don't understand. They're pretty fun. And they happen kind of naturally in a lot of different scenarios. And so the kind of standard scenario that we usually introduce with, the concept with, is something like this. Just grab this, bring it in. You want to fence in some area, but you only have so much fencing. What are you going to do? And so a backyard farmer wants to, let me see if I, oh, that's not it. And I had my panicky moment earlier. Let me just check here. It's recording. I'm not on mute. Feels good. Okay, there. Whew. Okay, so a backyard farmer wants to enclose a rectangular space for a new garden. She's purchased 80 feet of wire fencing to enclose 3 sides and will put the 4th side against the backyard fence. Okay, so what we want to do is we want to find a formula for the area enclosed by the fence if the sides of fencing perpendicular to the existing fence have length L. Uh-oh, everyone's favorite thing, word problems. I know. So just nice and slow here, right? Let's imagine the scenario first. So she's got the existing fence here. Let's start there. And then we're gonna have a rectangular space. So we can't have anything lopsided. We could handle that, but not as an introduction to quadratics. But we could solve it eventually, but not today. So what we want is we want some sort of rectangular area like this. And using our fancy terminology, find the formula for the area enclosed by the fence if the fencing perpendicular to the existing fence, it's hung up here. So if it's perpendicular, right, then we're talking about these fences here, the existing fences here, and these ones are going to have a length of L, both of them, right? because we said it had to be rectangular, so those are going to be a length of L. Okay. We only have 80 feet of wiring. Right? And so what's this length going to be? It has to be 80 minus L, right? Because we only have 80 feet. So here we have 80 minus L. You could write it as minus 2L right away if you want. But I like to just kind of go nice and slow here. So 80 minus 2L is that length. Okay. Why do we need that? We need it because our end goal is to find a formula for the area. Okay, so the area is, well, we know how to find the area of a rectangle, right? Length times the width. So here the area is going to be L times 80 minus 2L. I see it now. Why is this a quadratic? If I expand this out, I'm going to have L squared, right? And so what can we do? We can write the area is L times 80 minus 2L. When I have L as the variable inside my formula, usually what I do, or usually what we do, not just me, what we do is we say, this is a function, this is the area as a function of the length L. Area as a function of L. Right? Because L is the variable that's inside. So I can change L and I can find the area. Okay. Now, let's see here. So I have L times 80 minus 2, or I guess I should do it in the same order. L times 2L. It was kind of painful to do it that way because usually I like to have the coefficient out front. So let's rewrite it as 80L minus 2L squared. Or with decreasing powers, right? Negative 2L squared plus 80L. Okay. So now, find a formula for the area enclosed by the fence. We've done that. Nice. And the formula is, I'll do this, is a quadratic. That's all we were asked to do for now. For now. Okay. Good. Lost without my notes. All right. So you're in for a wild ride. Yeah, I said it. And I meant it. Totally lost, but it's all coming back to me. God, I don't have a photographic memory, but I can look at a sheet and I can remember what's kind of on it. Decent memory, I guess. Okay, so going back to last week, oh, we had a test last week too, but what would the general shape of this graph be? Okay, so here, if we consider the shape, maybe I'll use this here. So consider the graph. What would it look like? Well, if I have the area of L, right, the area is going to be our Y value, right? That's our output value. What's our input? Our input is the L, right? And so here we have the input is L and the output is the area. So what our graph looks like is going to look like this. We have L as the input and the area of L as the output. Knowing that it's a power of 2 or a degree 2, right? We know that it's got a general parabolic shape, but the negative flips it down, right? And so let's just, for the sake of argument here, draw it like this. So here, right, we've got a parabola flipped on the x-axis. I bumped it up because I want to have a positive area. And so I'm pretty sure that it's going to be bumped up like this. And so what we want to do is here we're increasing L, right? And so we're increasing the length of the sides. And as we do, the area is increasing until we hit the maximum, right? Which is also called the vertex. So here we have a vertex. And then what happens as I keep increasing the sides, what happens to the length in the middle? It has to get smaller and smaller and smaller. And so now all of a sudden my area is decreasing as I increase the length of the sides. So there is a value of L that maximizes the area. The area, let's see here. Can I squeeze it in? Yeah, the area. Okay. Okie dokie. So that's what we want, right? We want to maximize this area. We haven't been asked to, but I don't know, seems like a reasonable thing to want, right? And so how do we do it? We find the vertex. How do we find the vertex? Well, let me tell you. Let me tell you. Where is it? If we have, let me just bring this in here. If we have a quadratic function, we can write it in two different ways. Now, typically we write it like this, ax squared plus bx plus c, and that's what we call the standard form, okay? But we can also write it in this transformation form, which is a little bit kind of uglier looking, right? But it makes things more obvious, like, oh, I've moved to the left by 8 or to the right by h, right? And I'm stretching by a, and I'm going up by k. And so if we have the standard form, if we transform it into the transformation form, then why do we call it the transformation form? It's because it outlines the transformation from x squared to the standard form just explicitly. Okay? So the transformation form outlines the transformation, the transformation from x squared to ax squared plus bx plus c explicitly. If we have something like f of x is a times x minus h squared plus k, we're starting, we recognize that, okay, this looks like an x squared. So we start with a parabola, and the a, we only care about if it's positive or negative, right? If it's positive, it's pointing up. If it's negative, it's pointing down, right? But besides that, the stretch doesn't really matter. And so the next thing we're going to care about is moving to the right by h, right? And so here, we need to know if a is positive, which means that you have a parabola like this, or negative, which means it's going to be going down, right? Why would we care about that? Because it determines whether we want a minimum or a maximum or where the vertex is, right, relative to the rest of the graph. So that's good. We want to move, keep getting these mixed up. Shift right h units and up k units. Let's see, where's a color I haven't used yet? Purple. Up k units. If we let a be positive for now, let's just think about a basic parabola. So let a be greater than 0. Then I have something like this. I'm going to arbitrarily shift it to the right by h units and up k units, but it's still just a parabola, so it's shifting over to the right and then up k. And so here at some h k is the bottom or the vertex of my parabola. Vertex is at hk. What if we let a be negative? Okay, same thing, right? Now, if it's negative, I flip x squared on the x-axis, right? So starting at the origin, it's facing down now, and then I move it to the right by h and up by k. And so regardless, what's going to happen is, so you're going to start here, right? If a is negative, then it's flipped down, but then it's moved over to the right by h and up k units. And so let's see if I can move this. Oh, just one piece, I guess. Whee! Do a piecemeal. Aha. Those should have been hanging together, but you get the idea. So now the vertex is still at hk. Oops. Right? It's just a matter of whether it's a maximum or a minimum. Okay? And so here, in this case, of course, the vertex gives us the maximum. So here, this is the maximum. And here, this is the minimum. depending on the scenario, right? You might want to maximize or you might want to minimize. Is it possible to minimize the second one? No, right? Because it goes to infinite, or it goes to negative infinity in both directions, right? So you really only can maximize it here. Same thing for the first one. You really only can minimize it, because to maximize it, you'd have to go to infinity, right? And that's really hard / impossible. So, so we only have these two options. Okay? So if you want to maximize something, then that's a clue that your A has to be less than 0, right? Just kind of as a check your work situation, right? And so why do we need the vertex? We use the vertex. I'll say use or find the vertex in order to find the maximum or the minimum value. You know what? I'm going to even say maximized. Maximized or minimized value. You know what? Output. So specific. This in general, whenever we're maximizing or minimizing something, it's called optimization, and it's its own field of math. And those guys are pretty hardcore. So here, it's called optimization. They don't mess around. UBCO has a really strong optimization department, I guess. In case you're interested. Oh, that looks pretty fun, huh? Do more. Well, they're going to be working with something other than quadratics, I'll tell you that much, but the idea stays the same. So, pretty fun. All right. So, how can we find the maximized area of that function that we developed? Well, I had my formula like this, but I want it like this. Uh-oh, how am I supposed to do that? Well, there are a couple of different ways. Before I say anything else, let me see. Okay. Let me see here. Do we want to work through it together, or should I just copy pasta? Work through it. Oh, making me work for it. All right. So I guess first I should clarify that this, if we're looking for the vertex, right? If we're trying to maximize or minimize something, which is often what we're trying to do, then of course having it in this form is beneficial, right? But how do we get from here to here? Well, I think the easiest thing to do is to go from here to here and look at the relationship between the two, betwixt the two. Okay, so here I'll start on a new page. Moving between a times x minus h squared plus k and ax squared plus bx plus c. Okay. So if I have a times x minus h squared plus k, what can I do if I'm trying to morph it into something like this, the first thing I would probably do is expand the x minus h squared. That's a good place to start. So I have a times x minus h times x minus h plus k. Okie dokie, artichokey. Let's see here. Boil this out, right? And so I'm gonna ignore the a for a little bit and I get x squared. I like to do them, I don't get fancy with my FOILs, right? When I expand things out, I do it nice and slow and I do each term. If you're some sort of expansion whiz, then go for it. But I am not. I've been burned too many times. X times x is x squared. X times negative h is minus xh. Negative h times x, I'm going to write it as minus xh again because I want to collect like terms later. Negative h times negative h is plus h squared and then plus k. All right, just focusing on the x minus h expansion. All right. Simplify a little bit. A times x squared minus 2xh plus h squared plus k. Okay, looks pretty good. All right. So then, now I'm going to expand this a inside. Ax squared minus 2axh, because it's a personal preference thing, but I like to have my number, my coefficient out front, but then of course a is just a number as well, but I like to tuck it in behind, so I have 2axh. If you want to write minus a to xh, that's fine. I just can't bring myself to do it. Plus ah squared plus k. Okay. Okay. Do you see it? Little bit, that's good. Hey, I'm happy with that, right? And so here, let's just remind ourselves that only the x's are variables. Everything else, they're just numbers, right? They're just placeholders for numbers. And so what do I want to do? I'm going to, well, ax squared looks good on its own, right? And then I've got minus 2axh. That's just the x term. I shouldn't say just, but ah squared is just a number, and same with k, right? And so here, what I'm going to do is I'm going to rewrite this as ax squared plus, because if I want to make it look like this, right, then I have plus something, but if I am actually subtracting, then what? Plus negative 2ah times x, right? Trying to make it look like this, something times x, and then plus c, but the c is going to be ah squared plus k. So now I have ax squared plus bx plus c. A little bit nasty. Okay. Now what? If I have A, B, and C, right, that's usually the form that we're starting with, then what do I need to do? I need to rewrite C in terms of H's and K's, right? I have A is the same in both scenarios, and that's our lifeline, right? Is that A is A here and here. Okay, so that's nice. So what do we need? We force B to equal negative 2AH. which means that if we want to solve for h, right, remember we're looking for h and k because we already have, and let me just write that down. From ax squared plus bx plus c, we have a, b, and c. So we need to find, but for the vertex form, let me write that. But for the vertex form, or sorry, I call it vertex form, I guess, but it's technically transformation form. I'll call it vertex form in brackets. We need A, H, and K. Luckily, A is the same in both forms. Which means that now, so we need to find H and K. That's what we're going to do in terms of ABC. Okay. So here, right, we saw that, okay, this whole coefficient negative 2AH has to be the same as B. Okay. So if I want to find H from this thing, what do I have to do? I have to force B to be negative 2AH, and then I'm going to solve for H. So H is going to be B divided by negative 2A. Right. Divided both sides by negative 2A, but then I also did a switcheroo around the equal sign. But now we have H. Well, it's a lot of work, Emily. I know, I know. Notice how I'm not promising that it's on the formula sheet because I haven't double checked. I'm sure it is. This is insane. Who would make you do this or even memorize it? Who? Well, I'm not committing to anything. So now we know what H is, right? Because from our original form, right, ax squared plus bx plus c, I have B and I have A, and so I can find what H is. Okay. Now, same idea. I'm going to force AH squared plus K to be equal to C. And what am I going to look for? I'm going to look for K. But also remember that we just found H in terms of B and A, D and A. So now find K by forcing AH squared plus K is equal to C. What we're going to do is we're going to take this H. Oh, that was a little bit weird of me. And substitute it in, right? I know that H can be replaced by B over negative 2A.
I thought you wrote now hide K. Like, what's going on?
Yeah, now just tuck it away and forget all about it. That's also an option, but it's not going to get you very far. So if we have A times B over negative 2A squared plus K is equal to C, I can expand that square in because I'm just multiplying and dividing inside the bracket, so I'm allowed to do that. So the square goes on the B, it goes on the -2, and it goes on the A to get me to a new page. Gonna start it fresh here. Maybe even move over. No. So I have A times B squared over -2 squared times A squared plus K is equal to C. Okay. A is going to cancel with the A squared, right? And so I'm going to be left with just one A in the denominator. And now I have B squared over 4A plus K is equal to C. But I'm trying to solve for K. And so K in terms of A, B, and C. Now solve for, what color did I use? Same. Solve for K. I get K is C minus B squared over 4A. Could put it over a common denominator, but I think we'll leave it there. Okay, how about an example? How do we use this? Did I bring in the formula sheet? Let's check. Oh, just the test one formula sheet, huh? Let's see here. Full formula sheet. Hope it's on here. Sort of. Sort of. Okay, it's sort of on there twice, but we're not there yet. Sort of. I feel like I'll add it. It's one of those things that you're supposed to know, but I don't find that there's any value in memorizing this thing. If you write it enough times, you will have memorized it. That's the curse, isn't it? So therefore, from ax squared plus bx plus c, we can rewrite the quadratic in the transformation form, but let's just call it in the form a times x minus h squared plus k. Oh, doesn't want to keep up. By finding h equal to b over -2a b, and k equal to c minus b squared over a. Okay. All right. So now let's see if I can grab an example. Ooh, maybe in the, ooh. Sketch a graph. Hey, we didn't do all these. Oh, find the vertex. Oh, nice and slow. I think I took off with you guys. Supposed to find the vertex of something easy first. That's fine, that's fine. We had to warm up. We got there. Took off like a horse. Okay. Let's start nice and slow. Why do I call this nice and slow? Because it's already in that transformation form, right? And so here, this is already in the form a times x minus h squared plus k. Now, if we want to find the vertex, if we have it in this form, is going to be at hk, right? And so the vertex is at hk. That's just a fact. If you have it in that form, you can just grab the h and the k. And that's why we wanted to find h and k from the more complicated version, right? And so if the vertex is at h and k, let's just remember that you need to have a negative here. So if there's a positive, then the h is negative, right? But in this case, it's a nice example. So here we have a is 2, h is 3, and k looks like 1 plus k plus 1 looks good.
So it's just opposite for h, like you want it to be negative, so it's.
Yeah, so it has to match the x minus h. And so if.
So if it is positive, then it's negative h?
Yeah, then the h is negative.
Yeah.
Yeah, nice.
Okay.
I'm sure there's one lined up. Otherwise, I'll do it. I'll make one up. I'm not scared. So then the vertex, right, just knowing h and k is at hk, which is at 3, 1. We can confirm it using Desmos if we want to have a look at it, right? So if I want to graph, 2 times x minus 3 squared, step it down, plus 1, then it gives me the vertex, and I'll try to make it a nice and small screenshot here. Crop top. Hey, I had it clicked, but this is at 3, 1, which confirms what we found. Right. Nice. That's all we had to do there. Let's see, I'm pretty sure he's gonna have, oh, doesn't. I'll make one up. Find the vertex of, should we go crazy? -3x plus 2 squared minus 1. Double whammy. Right? Remembering that general form of a times x minus h squared plus k. You're trying to match these up. And so we have a is equal to -3, which in our minds right now, it's a parabola facing down. And so the vertex is a maximum, right? But we're just asked to find the vertex. And so x minus h, but x plus 2 is equal to x minus h. If you wanted to, you could say x plus 2 is equal to x minus h and then solve for h. That's a surefire way to do it. X plus 2 is equal to x minus h. I can subtract x from both sides to get rid of the x's. And so then 2 is equal to -h. But I want to solve for h, not -h. So therefore, h is -2. That way is always going to work, because then you don't need to look at this and say, okay, plus 2, then h is negative, right? But the h value is 2, right? We're just trying to figure out if it's positive or negative. And if it's positive plus here, then it has to be a -h. So h is -2 and plus k is plus -1, right? And so my k is -1, but how can I write that? So I have -1 is equal to k. I guess that's it. Wah, wah. Thought I was gonna have to do something. No, just -1. Okay. So it's this one that requires a little bit of work. But if you just see it, you don't have to show this work. I just want to show you what you're technically doing. Right. Okay. Let's go back here. Grab this. So we already found this. We did the work. So for a quadratic given in standard form is that ax squared plus bx plus c, right? Then the vertex hk is located at, h is at -b/2a, that's what we found, and k, which is at f of h, which is the function evaluated at -b/2a, but we actually found what it is. It's going to be c minus b squared over 4a. But this way you only have to memorize one thing, I guess, sort of. Not really. Okay. Are we ready to do that? We've waited long enough. Let's do this one. Find the vertex of g of x is equal to 2x squared minus 12x plus 1. First thing we're going to do is identify our A, B, and C. All right. And so here, find A is equal to 2. B is negative 12, right? Because it's ax squared plus bx plus c. And then c is equal to 1. If we want to find the vertex, right, really what we're looking for is the point hk, which means I have to find h and then I have to find k. Okay. And so our h's are the same, right? The h that we found was negative b over 2a, and here the h is negative b over 2a. And so regardless how you find h, doesn't matter, you're going to get the same, right? B over negative 2a is negative b over 2a. This negative can be in any position, means the same thing. That's confusing, I think. But let's focus here first. So H is, I'll put the negative out front, negative b over 2a. I have b and I have a, so H. And if you think about the vertex is supposed to be a point, right? So the h and the k, they're going to reduce down to just numbers, right? Just two values. And so you've done the hard part, I think. Now we just plug and chug here. So negative 12 over 2 times 2, which puts me at h is equal to negative 12 is 12, and then divided by 4 is 3, yeah? 12 divided by 4. Sold. No complaints. All right. All right. So for K, though, what they're showing is slightly different than what we arrived at. I want to do both to convince ourselves that they are the same. And let's see here. First, I'll grab, let's call it our way. Copy. So K is C, which is 1, minus B squared, which is negative 12 squared. Careful with your calculator, because some calculators, and I don't remember how ours works, but if you just do negative 12 squared, it gives you a negative number, but that's not true. So you have to put the negative 12 in brackets before you square it. And so let's see here. I've got C is 1 minus negative 12 squared divided by 4 times 2. I'll use my trusty calculator because I don't do that. Let me try it though. Negative 12 squared gives me negative 144. That's bad, right? Squaring any value is going to make it positive, right? Thinking about the parabola, no matter what value of x you give it, it's going to be a positive output, right? And so it's going to be 144 divided by 8, which gives me a nice 18. 1 minus 18, which I am confirming. Yes, negative 17. Okay. Let's have a look at this thing and just make sure I didn't mess anything up by graphing this thing.
You got 4 times 2 for K, but
yes, C is 1, B is -12, and then 4 times A, which is 2. There you go. Yeah, you want to keep them separated. Yeah. Okay, what was I going to do? I was going to graph this thing. Make sure I didn't mess anything up. Maybe don't write anything down until I've confirmed it, okay? Feeling pretty good because I'm not getting nasty values, but that doesn't mean anything. 2x squared minus 12x plus 1. Okie dokie. 2x squared minus 12x plus 1. Feeling lucky. Woo! Yeah. Try to get this. Hopefully it keeps the, yeah. What a disaster that would have been if I had mucked it up. Totally bungled it. I didn't. All right. What are they going on about? F of h. K is equal to f of h. Well, if we kind of take a step back, then if the vertex has an x value of h, then, right, if the x value of the vertex is h, then k must be g of h, right? It has to be the output of the function at h, right? And so that's where this came from. And maybe that's a little bit nicer to kind of work with, maybe not. I don't know. So from here, maybe I'll explain that a little bit. Notice the vertex at HK, right? Has x equal to h, which means we can find g of h, right, as the output when x is h, as the output when x is equal to h, which means that k is equal to g of h. So if we're able to find h, which we did, right? Pretend that we didn't do this part. This was from our derivations, right? We found this formula for k and it works, right? But what if we only had h is equal to 3? Now what can I do? I can say, okay, well, at x equal to 3, I can find the output because it has to be on this line, right? And so now what I can do is I can find g of 3, and that's going to be the k in our vertex, right? The output in our vertex. So since we found h is equal to 3, k is g of 3, which is going to be, I lost it. 2x squared minus 12x plus 1. 2 times 3 squared minus 12 times 3 plus 1. Math. I'm going to guess -17. Just a lucky guess, you know. 3 squared times 2 is 18. Minus 12 times 3 is 36 plus 1. Whew! Feels good when you don't muck it up. -17. So therefore, the vertex is at H, f of H. I guess we had G, but doesn't matter generically. G of H or HK if you prefer. But in the end, it's going to be at 3, -17, as we saw in the graph. Okay. What else could we do? Knowing what H and K are, I can rewrite from the standard form into the transformation form. Okay. So knowing H and K, we can rewrite 2x² minus 12x plus, was it +1? Yeah. In transformation form. The A is the same, right? Transformation form in general is A times x minus h squared plus k. We know h and we know k, so here we go, and A is the same. So A, let's see here. A is 2 times x minus h, which we found was 3 squared minus 17. Which we could use to easily find the vertex if we had it like that, right? But in the end, we're chasing after these h's, and then the h is going to lead us to k because that's just the output at h, right? Let's just graph this to make sure that they're the same. Be really bad if they weren't. Really bad. Put it on the same graph here. 2 times x, oops. I want the bracket. X minus 3, bracket squared, minus 17. Phew. So I can flip between the blue and the green, and they're the same. And that's a good thing. So regardless of the form, they'll be the same. Same graph, right, for these two. Whoa. Arrows all over the place. All right. Which is good. Means that they're the same. Okay. I think that we should not complete the square yet. I think that we should go back to that original problem, which we found the area for, and let's find the maximized area, right? What length of the sides do I need to maximize that area of the rectangle? So now, going back to the original example where we found the area as a function of L was -2L squared, I think. Scroll all the way back up. Whee! -2L squared plus 80L. -2L squared plus 80 L. What if we want to maximize? So what value of L maximizes the area? What value of L maximizes the area? That's a reasonable thing to wonder. So now, right, if we go back, doesn't hurt to think about it again, or maybe it does. I've got some length L and the output, the area of L. And so we want to find at what value is this thing maximized. Luckily, it's a parabola turned down. And so it's going to have some maximum value at the vertex. The vertex is the maximized area. Okay. Unfortunately, we have this thing in standard form. That's a bummer, right? If we had it in transformation form, we could just grab H and K and be done, but we don't. But we have the tools. And so let's just make a note here. This is plus 0, right? Which means that your C is 0. So from A of L equal to negative 2L squared plus 80L plus 0, A is negative 2, B is 80, and C is 0. We can find H by negative B over 2A. See, it's not so bad. Maybe you don't need it on your formula sheet.
So we don't need to do all that middle work then. We just have to use those two
Yeah.
formulas that we figured out. Okay,
Yeah.
good.
It's just holding your hand through it. Hey, you guys said, let's work through it. All right.
Yeah, that's so sad. Oh my gosh. That's so
You'll feel like a champ though, working through all those.
bad.
But it's really hard, especially going the other way. It's easier to work from the transformation form to the standard form. So that's why we went that way. But now that we have the formulas for H and K, and we really only need H, then we're good. Then you can just forget all the rest. Well, maybe don't forget it, just parking lot it. So then here, H is negative B over 2A, right? Which in this case, H is negative 80 divided by 2 times negative 2. Now, those negatives are going to cancel, which is nice. I don't know why. I always need my calculator, but I shouldn't have needed it there. 20. Okay. I know I'm running out of time. What's my K? Well, if the H, which is really just the value of L that maximizes the area, right? So here, what we're saying is that H is 20, right? Going up here. Then what we want to find is K, which is really A of 20, right? Or A of H. So K is equal to A of H, which is A of 20, which we can do the area of 20. Well, now you've got 20 and 80 minus 40, and then don't do that one. And then you multiply them, right? Or you can use the formula negative 20, 20. Is it negative 20? No. Too many 20s. Negative 2 times 20 squared. Oh my gosh. Plus 80L plus 80 times 20. 20 squared, 400 times negative 2 plus 80 times 20. I get an area of 800. So here, oops. A of 20 equals 800. We can confirm it with my last 2 minutes. Boop, boop. Negative 2x squared, because the x is just the L, plus 80x. I'm gonna have to zoom out a lot, right? Because I know that the vertex is at 500. Whee! Or sorry, 800. 20, 800. Wow, we did it. Oh, except it didn't keep the vertex, which is at 20, 800. So then the area is maximized at a length of 20, and the area would be 800. Therefore, the maximized area is 800 square feet, I guess, but I'm not, don't tell Sydney, but I don't care about units. Or Allison for that matter. Don't tell anyone, okay? All right. Any questions? No? Just need to think on it, stew on it a little bit. If you have any questions, let me know. If you didn't get your test back yet, come grab it. I'll see you on Wednesday. I feel like I've forgotten something, but